Now, it's often necessary to have two cylinders which operate in sequence. That is, one must complete its stroke before the other begins. An example might be a clamping cylinder and a work cylinder. Naturally, we'd have to clamp first, but fluids take the course of least resistance. And if the work cylinder moved easiest, we'd be in trouble. Such an application calls for a sequence valve, which will not only assure that the clamp moves first, but also maintain sufficient pressure to hold the workpiece as the second cylinder approaches. This time we'll use a single directional valve to control both cylinders. The sequence valve, which is held closed by an adjustable spring, will prevent flow to the work cylinder until the clamp is firmly in position. When pressure reaches that required for clamping, it will overcome the sequence valve setting and permit flow into the work cylinder. Pressure in the clamp cylinder will be maintained at the sequence valve setting regardless of how easy the work cylinder moves. However, as pressure in the work cylinder builds up beyond the sequence valve setting, the clamp pressure will also increase. Sometimes, to avoid crushing the workpiece, a pressure-reducing valve is used to limit clamping pressure to a safe maximum. A pressure-reducing valve is held in its normal open position by a spring and is closed by pressure sensed at its outlet port. With a sequence valve and a pressure-reducing valve added to our circuit, we can not only cause one cylinder to move before another, we can maintain pressure on it between set minimum and maximum levels as the second cylinder performs its function. Now, let's try a rapid traverse and feed circuit. They're quite common in machine tool applications for drilling, tapping, and similar functions. Since the work will be done on the extending stroke, we'll use a long cylinder with a single rod. In order to be able to stop in mid-stroke, we'll need a three-position directional valve, which is spring-centered with at least the cylinder ports blocked. Next, a large volume pump to provide the speed we'll need in rapid traverse, and the ever-present relief valve. Have you noticed these are the same basic units we used before? This time we'll put a flow control in the exhaust line from the cylinder. A drill might pull ahead as it broke through the work, so a meter-in or bleed-off circuit wouldn't do. We now can control the cylinder's speed during its entire extending stroke, but that's not quite what we want. We need to move up to the work quickly, then slow down just before the drill contacts the work. To do this, we'll use a cam-actuated shutoff valve that's normally open. Its proper name is a deceleration valve. We'll place it so it can be closed by a cam on the cylinder rod and pipe it so flow can bypass the flow control during the rapid approach to the work. By properly locating the cam, it will cause the cylinder to decelerate and feed into the work at the flow control setting. Both flow controls and deceleration valves are available with integral check valves for reverse free flow. But we'll place one here for the sake of clarity. It will bypass both valves for a rapid return stroke. As we mentioned, this circuit is typical of many applications where a large volume of fluid is required at low pressure to move quickly up to the work. Then only a small volume at high pressure is needed for the work portion of the cycle. With the single pump selected, the bulk of its delivery is not being used during the feed portion of the stroke. As a result, it returns to tank through the relief valve at its setting, and a great deal of energy is wasted. I might not have mentioned this if we didn't have a fix, but luckily we do. It's called an unloading circuit, and it uses two pumps, one large and one small. The small one needs only enough volume to supply a little more fluid than our system requires at high pressure. The large pump will help out when the going is easy, during rapid approach and rapid return. To complete our package, we'll need an unloading valve and a check valve. The two pumps piped together will replace the single pump and provide the large volume required at low pressure. When the pressure builds up, as it will when we go into the work portion of the cycle, the unloading valve opens, permitting the large pump flow to return freely to the reservoir. The small pump, however, cannot get through the check valve and continues to operate up to the relief valve setting. As the cylinder returns at low pressure, the unloading valve closes and the large pump volume again joins the small one for a rapid return. Come to think of it, we not only save energy with this circuit, we can usually get by with a smaller electric motor. With a single pump, the motor has to drive its full volume up to the relief valve setting. Using two pumps, the motor drives the combined volume up to the unloading valve setting. The large pump delivery then goes to tank at little or no pressure, and only the small pump goes to the relief valve setting. Now, how about another application? A hydraulic curing press. Here again, we'll need a lot of oil to close the press quickly, then a small amount at high pressure during the curing cycle. Sounds like another good application for an unloading circuit, and it is. But we're going to try another approach, an accumulator, a device for storing oil under pressure. First of all, we're going to need a pump, relief valve, directional valve, and cylinder. If we select an 8-inch diameter cylinder, it will have an area of 50 square inches, and at 1,000 psi will develop a force of 50,000 pounds, or 25 tons. A 15-inch stroke would require 750 cubic inches, or 3.25 gallons of oil. So a 20-gallon per minute pump would close it in 10 seconds. We'll use an open center valve, but put a counterbalance valve in the line from the bottom of the cylinder. It does just what its name implies. It counterbalances the weight of the press platen and keeps it from falling. We're now able to open and close the press and build up to 25 tons of force. But to hold it for several minutes would have our 20 gallons per minute pump running at 1,000 psi, with most of its delivery going back to tank through the relief valve. And that's not practical. We'd be wasting nearly 15 horsepower. Now, this is where the accumulator comes in. We tee the accumulator off our main supply line between the relief valve and the directional valve. It has a bladder in it, something like the one in a football. Next, we'll pressurize or preload it with dry nitrogen to about 600 psi. This time, when the press is fully closed, instead of going over the relief valve, the oil will start filling the accumulator from the bottom and compressing the gas even more. By sensing the pressure with a pressure switch, we can actuate a small solenoid valve and vent the relief valve when the pressure setting is reached. A vented relief valve opens at very low pressure, permitting the pump to flow freely back to the reservoir. A check valve placed upstream will prevent backflow from the accumulator, and the compressed gas inside will maintain pressure in the rest of the circuit. Any drop in pressure can be sensed by a pressure switch, which at some predetermined minimum pressure will energize a solenoid valve and devent the relief valve. The pump flow will again be directed into the accumulator, but only long enough to replace the fluid lost through leakage, and the cycle will repeat. In this way, the pump will operate under pressure for only a few seconds during the entire curing cycle.